아마 폐강은 안 될 겁니다. 지금 두 명이 그 회사 다니시는 분이래 갖고 자주 못 오셔갖고. So in the last lecture, I introduced some quantity, right? Physical quantity. So there have been three different physical quantity. One can be described by scalar, and also some can be described by vector and matrix. And scalar vector matrix have some relationship among these. So scalar is just a real number, one number, and vector it consists of many number. So it can be said the array of number, array of scalar, and matrix is an array of vector. So we can generalize this concept. So we can think the array of matrix or array of matrix. So now I like to introduce the tensor. What is tensor? Tensor is a really generalized quantity. So in many the paper for mathematics and engineering and mechanics, the people like to use a tensor instead of a vector and matrix. So we can think tensor is a sum of scalar vector matrix and more. So tensor includes all these three and then more. So tensor includes the scalar and vector and matrix and more. So tensor is a superset of all the quantity. So especially we are saying the scalar is zeroth order tensor, vector first order, matrix second order. So there are going to be a third, fourth, and many. So nth order tensor. So we can think nth order tensor, right? So tensor is a generalized quantity. Quantity. So many students think the tensor is a very difficult one, complicated, hard to understand. So they don't want to understand the tensor. So let me introduce the tensor little by little. So we can make a diagram, something like that. This is tensor. Okay. And here we have matrix. And inside of matrix, vector and scalar. If the vector have only one component, okay, that become a scalar, right? So scalar is included in the vector. Also, if the matrix have only one column, it's just vector. So vector is included in the matrix. So relation is something like that. Then let me review vector algebra. You know how to define and how to use, how to manage the vector, right? So this is a vector which has only two components. 3 and 5 is real number, and this is a real vector. If the 3 and 5 is a component of this vector, right? If the component is the complex number, then we can also define the complex vector, right? So vector can have many different number inside of a bracket. Something like that. This is also vector, right? So vector can have n ordered number inside of a bracket, right? And especially in all the kind of vector, let me focus on the geometric vector x, y, g. This is a geometric vector. So we can also say x1, x2, x3. This is a geometric vector in 3D. What's the geometric vector? Geometric vector have only 3 components. It has 3 number. So x, y, z. But this is a coordinate. So this geometric vector is very important in physics and mechanics because the geometric vector can describe any position in 3D space, right? In this room, okay, at this point, there is some point. I like to define the position. Then I should use at least 3 number, right? About x-axis, y-axis, g-axis. And also, instead of x, y, g, people also like to use x1, x2, x3. Same thing. So x1 is x, x2 is y, x3 is g. So to define the geometric vector, first of all, we need to define the coordinate system. So this is for example, Cartesian coordinate system. So Cartesian coordinate system is very widely used in engineering. This coordinate system is defined by origin. This is origin, O, and 3 base vector, E1, E2, E3. So these 3 base vector define the coordinate system. These 3 base vector have a unit magnitude. So lengths of the E1, E2, E3 are 1. And 3 vectors are normal to each other. So angle between each vectors are 90 degrees. Okay? So normal to each other. So we are saying this kind of coordinate system is Cartesian. Okay? So when we have some point here, okay, this is x. How we can go to this point from the origin? We are going in E1 direction. The amount of this point, the distance is x1, and E2 direction x2, and E3 direction x3. Okay, and this is a distance vector x. So we can to go the position here from the origin, we can go three way in E1 direction, E2 direction, E3 direction. Also, we can go E2 direction first, okay? And E1 direction and E3 direction. Also, we can go E3 direction first. So E1 direction next, E3 directions. So anyway, we can go to same position. Here the E1, E2, E1, E2, E3 is a base vector. Base vector of the Cartesian coordinate. Okay. So let me give you two examples. Okay, here I have some position 1, 1. Let's say I don't have a coordinate here, number. So what's the x for this point and y for this point? What's the x1 and x2 for this point? Can you give me a number? No. Why? Because we do not define the coordinate, right? So let's think I define the coordinate here. This is E1, E2, into. This is a unit vector, 1, 1. This is normal. So to find the coordinate mean the x and y, or x1 and I need to go to in E1 direction first. So 1, 2, 3, 4. So, and 1, 2, 3, 4, 5. So, this coordinate for this position is 4, 5, right? Then, if the origin is here and Cartesian coordinate system is something like that, okay, E1. E2. What is the coordinate? Let's say this is the other coordinate. So we need to go 1, 2, 3. So -3 and 3. Let's say 3, 3. So x and y are totally different. So it depends on how we choose the coordinate system, right? If the coordinate system change, the coordinates x and y, the vector, component of vector, number in the vector are changing. So when we use the geometric vector, we need to define the coordinate system first, right? So okay, so the geometric representation of vector x completely depends on the coordinate system you choose, right? And also, I only here introduce the Cartesian coordinate system. It has a 3 base vector, 3 unit vector, and all the vectors are normal to each other. So that the Cartesian and usually the most of us are very familiar with the Cartesian, but there is not only Cartesian. So base vector don't need to be unit. Okay? So this is let's say this is the other base vector. Let's say this is B1. This is a B2. Okay, this is not 90 degrees, and length is not 1. Okay, this is a alternative coordinate system, right? But it works. So this is a more general description of a coordinate system. So base vector doesn't need to be unit and doesn't need to depend normal to each other. This is a much more generalized system. So for example, but in this system, how we can define this point? So we can define this point. So we go in this way. So this is the way, direction in VT, this is direction in V1. We go to the V. So we go in V2 direction. Let's go V2 direction, 2, 3, 4, 5. And then we go to V1 direction, 1, 2, and half, maybe half. Then here coordinate become -4 and 2.5, something like that. So with only this number, it's impossible to define some position. So when we define the position, we need to know the coordinate system, we need to know the base vector, right? So when we write down the vector. We need to write down the base vector together. So first, let's consider this first one. First case here. X equal, okay, 4E1 plus, right, 5E2, right? We go to the E1 direction with a distance 4. We go to the E2 direction with a distance 5, right? This is a second description. X equal 2.5 B1 minus 4 B2, right? Both are same thing. Yeah, let's look at the here. So first one is X vector, so second is X vector, right? So in general, X can be any position vector can be expressed by x1 b1 plus x2 b2 plus x3 b3, or summation I equal 1 to 3 xi bi, right? Here we are saying the okay. Xi is a component. Bi base vector. Okay. So position vector, geometric vector X is a sum of the component multiplied by base vector, right? This is general form. And usually people don't want to write down this part, right? So people just like to write xi bi. Sorry, here I need to have a vector. This rule is named summation convention or Einstein convention. So if you look at the mathematical description looks like that, then you can think the summation character is omitted. The name of this notation is compact notation. Compact notation. In mechanics, solid mechanics and fluid mechanics, we are use this compact notation. And here we are name of I is a dummy index. Or pre-index. This R is changing from 1 to 3, right? So x equal xi bi. This is a tensorial representation of a vector. Yeah, this is tensor xi and bi. That's a tensor. Here. In the Cartesian coordinate system. So x is a geometric vector, can be represented by xi, ei. And for example, u is a displacement, ui, ei. A is a velocity, ai, ei. Something like that. But usually, when the coordinate system is freely defined, so everybody know the coordinate system, right? We don't need to write down the base vector. So when the coordinate system is given, so everybody knows the coordinate system, then we can just write down xi instead of x vector, u, ui, a, ai. So we are write down the x vector like this, xi. Xi just become an x vector. Yi just become a y vector. Ai is become a vector. Something like that. Okay. This is a tensorial representation. Okay, this is a tensor, all the tensor. Xi, ui, ai are tensor. Tensor is not a very, complicated thing. Using the tensor, we can do manipulation of a vector. First of all, sum. So vector C equal vector A plus B, right? When we use this calculation in engineering, okay? Yeah, for example, A is some force in this direction with some magnitude. B is some force in this direction. If you sum both force vector, we can make a resultant force, right? So C equal CI EI, right? This means C1 E1 plus C2 E2 plus C3 E3. And A vector is the same. A1 E1 plus A2 E2 plus A3 E3 B vector. B1 E1 B2 E2 B3 E3. Let's plug in this equation into the here. Then what happened? C1 E1 plus C2 E2 plus C3 E3 equal A1 plus B1 E1 plus A2 plus B2 E2 plus A3 plus B3 E3. Right? Then let's compare the left-hand side and right-hand side. Right? If you compare left-hand side and right-hand side, we can easily find C1 should be same to A1 plus B1. Right? And C2 should be same to A2 plus B2. C3. A3 plus C3. So, in tensor form, we can write down these three equations with just one equation. Ci equal AI plus BI. BI. So instead of this equation, we can use this equation. Exactly same thing. Okay? And scalar multiplication. So B equal alpha. Alpha is scalar A. In tensor form, how can we write? Okay. You can easily do that, right? So BI equal alpha AI. You can very easily prove using the method I show showed you over there. Dot product. Or scalar product. Alpha equal A dot B equal A vector magnitude of A magnitude of B and cosine zeta, which angle zeta is the angle between A and B vector, right? This is the same to the A1 B1 plus A2 B2 plus A3 B3. Sum I equal 1, 3. AI, BI. Right? Here the A vector have a 3 component, A1, A2, A3. B vector have also 3 components. B1, B2, B3. So here we are using Einstein convention and then get rid of this sum. So finally, alpha equal AI, BI. This is a tensor form of dot products. So even if in this equation, on the right-hand side, we don't have this sum, but we need to know sum is omitted. So to understand this equation, we need to put the sum. Okay, when we think, but this and these equations are different. What? This equation is just one equation, right? This is one equation. But this equation means 3 equations. I is changing. So in this equation, I is in left-hand side, both in left-hand side and right-hand side. So it's changing. So this is not equal to sum CI equals sum AI plus sum BI. This is not the same. If the index is left and right-hand side, okay, index is changing and number of equation increasing. So this is the case when the I equal 1. This is the case is I equal 2. This is the case is I equal 3. So this equation means 3 equation. But this equation means just 1 equation. Okay? This is just common rule. Okay, cross product. This cross product is a little bit tricky. cross product. We are saying this is also vector product. Yeah, dot product and cross product. Dot product result in scalar. Cross product result in vector. So the other name of dot product is scalar product because this manipulation of vector A and B give us just a number, scalar number. But cross product give us a vector C equal A, B, right? And magnitude become A, B, sine theta, A, B. Direction. A, B. Direction is a normal to the surface defined by A and B. So, two vector A and B will define some plane, right? Some plane surface. And then direction of C is normal. So, something like that. This is direction. And C is A2, B3 minus A3, B2. E1 plus A3, B1. A1, B3. E2 plus A1, B2 minus A2, B1, E3. And this become C1, this become C2, this become C3. When we use the cross product in mechanics, when we use this kind of operation, never used before, we are using that kind of thing in solid mechanics and structural mechanics and fluid mechanics too, right? When we calculate the moment, right? Momentum or moment, we use this calculation. Also, when we use the rotation of some particle, we are using this cross product. And also, when we use the dot product over there, scalar product, in mechanics, energy calculation, right? If we multiply the pulse and displacement, it gives us energy, right? So one is a pulse vector, displacement vector. If we take the dot product of a pulse vector and displacement, it gives us energy, right? So used in mechanics, dot product is a very, very frequently used to calculate the energy. And also cross product is used to calculate the rotation of a particle and moment. So in tensorial rotation, we are using I, J, K, A, J, A, K. For cross product, we are using this. Here with E, I, J, K. This is a name, is a permutation symbol. Its definition is it becomes 0 for I and J is same, J and K is same, or K and I. So among the I, J, K, two of them are same. This permutation symbol gives us 0. And it gives us 1 for I, J, K is one of these. 1, 2, 3, 2, 3, 1, 3, 1, 2, and minus 1 for I, J, K is a sum one of this set 1, 3, 2, 3, 2, 1, 2, 1, 3. Something like that. Yeah, looks become very complicated, but you can easily understand. So 1, 2, 3. So I, J, K have order in this direction. Okay, 1, 2, 3. So 1, 2, 3, 2, 3, 1, 3, 1, 2. If I, J, K have a ordered number, which have order in here the clockwise direction, then it gives us 1. Counterclockwise direction, it gives us minus 1. So you don't need to memorize this, okay? Okay, any question?